Claude Agent SDK hooks. Permissions? Ask the model for permission. Hooks do not ask anyone. Part 8. How to put deterministic, non-negotiable guardrails into your AI agent, block destructive commands, inject live context, and audit every edit, no matter what the model decides. In this video, you will learn what hooks are in the Claude Agent SDK, why they sit a level below permissions, and how they give you the final word on agent behavior. We walk the lifecycle events in firing order, build the 3 hooks every team eventually wants, block a dangerous command, inject live context, audit every edit, and cover the gotchas that matter because hooks run inside your own process. Let's get started and show how hooks can block certain tool calls and actions deterministically. Part 8 of Building with the Claude Agent SDK, a 14-part guide to building production-ready AI agents. You can give an AI agent a careful set of permissions and still lose. Permissions are real and they help, but they share a property with everything else the agent does. They pass through the model's judgment and your approval prompts. The model decides what to attempt. You decide whether to approve. Both of those are judgment calls, and judgment calls fail. A hook is a different kind of thing entirely. A hook is your code running at a fixed point in the agent loop, executing every single time, regardless of what the model wants or which permission mode you are in. If a pre-tool use hook says no to rm-rf/, the answer is no, full stop. No prompt, no model discretion, no clever phrasing that talks its way past the guardrail. This is the moment you stop configuring an agent and start controlling it. Hooks let you block dangerous operations before they run, inject fresh context into the conversation, transform tool inputs on the fly, and audit everything for compliance. This article walks the lifecycle events in the order they fire, builds the 3 demos every team ends up wanting, and then spends real time on the gotchas, because hooks run inside your process and the failure modes are particular. How a hook fires. Before any code, it helps to see the whole mechanism at once. A hook firing is a 5-step pipeline. An event fires, a tool is about to run, a prompt was submitted, or the session just started. The SDK collects the hooks registered for that event. Matchers filter which ones actually run, narrowing by tool name. Each matching callback executes, receiving a typed input object with the event details. Finally, your callback returns an output object that tells the agent what to do: allow, block, modify the input, or inject context. You register hooks in the hooks option, keyed by event name, each wrapped in a hook matcher in Python or a matcher object in TypeScript that optionally narrows by tool. A matcher of write, edit runs only for those 2 tools. Omit the matcher, and the callback runs for every occurrence of the event. One limit is worth fixing in your mind early. Matchers filter by tool name only, not by file paths or arguments. To act on a specific path, you check tool input inside the callback. The matcher gets you to "this is a write." Your code decides "this is a write to a path I care about." The events in the order they fire. Across a single run, hooks fire at a set of predictable points. 6 of them form the backbone. Session start runs once when the session begins, which is the natural place to load state or warm a cache. User prompt submit runs when a prompt is submitted before the model sees it, which is your chance to inject context. Pre-tool use runs before every tool call and can block or modify it. Post-tool use runs after a tool returns with the result in hand. Stop runs when the agent finishes, which is a good place to save state. And session end runs at teardown. There are more events beyond these 6, including post-tool use failure, sub-agent start, sub-agent stop, and pre-compact. But the 6 above carry most of the weight, and 2 of them, pre-tool use and post-tool use, do most of the real work. The demos start there. A Python gotcha worth knowing before you write a line of code. The Python SDK does not support session start or session end as callback hooks. Those events, plus several others, are TypeScript only in the programmatic API. In Python, you get them only as shell command hooks configured through settings files, loaded via setting sources. If you reach for a session start callback in Python and it never fires, this is why. Pre-tool use, post-tool use, user prompt submit, and stop all work as callbacks in both SDKs. Demo 1. Block a dangerous command, no matter what. This is the headline use of hooks. A pre-tool use hook on the bash tool inspects the command and blocks anything destructive. Because this runs before the permission mode is even consulted, where hooks are evaluated first, it holds even under bypass permissions. This is the safety net that does not depend on the model behaving. The callback returns two things together: a permission decision of deny inside hook-specific output to stop the call, and a permission decision reason to tell the model why, so it does not simply retry the same thing. The top-level system message is for the human watching. It surfaces a message to the user, not to the model. Here, we're looking at a simple but powerful safety hook for an AI agent. This function runs before the agent uses the bash tool. It takes the incoming tool request, pulls out the shell command, and checks whether that command contains rm-rf. That matters because rm-rf is a classic destructive deletion pattern. It can recursively delete files and directories without asking for confirmation. In a production agent, that is exactly the kind of operation you do not want the model improvising with. So the hook acts as a hard guardrail. If it sees rm-rf, it returns a structured response that denies the tool call. The system message is the human-facing message. It tells the user, blocked a destructive command. Use a scoped, reversible deletion instead. The hook-specific output is the part that actually controls the agent. It includes the hook event name, sets permission decision to deny, and gives the model a reason. rm-rf is not permitted. That reason is important. It helps the model adapt instead of retrying the same dangerous command. And if the command does not contain rm-rf, the function returns an empty object. In this SDK pattern, an empty object means allow the operation unchanged. The big takeaway is this: permissions ask whether something should be allowed. Hooks enforce what must never happen. This hook gives your application the final word before a dangerous bash command can run. This is the TypeScript equivalent of the Python hook we just looked at. It does the same job. It runs before the agent uses the bash tool, reads the command from the tool input, and blocks the command if it contains rm-rf. The main difference is TypeScript's typing. We import hook callback and pre-tool use hook input, then cast the incoming hook input so TypeScript knows this is a pre-tool use event. We also cast tool input as a generic record so we can safely pull out the command field. From there, the behavior is the same. If the command includes rm-rf, the hook returns a system message for the user and a hook-specific output object that denies the tool call. The permission decision reason tells the model why the command was blocked, so it can adapt instead of retrying the same destructive action. If the command is safe, it returns an empty object, which means allow the operation unchanged. So conceptually, there is no big difference between the Python and TypeScript versions. The structure is the same. Inspect the bash command, deny dangerous operations, and let safe commands pass through. After defining the hook, we register it with the agent options. Here, the hook is attached to the pre-tool use event, which means it runs before a tool call is executed. The matcher is set to bash, so this hook only runs for shell commands. It will not fire for file edits, reads, web calls, or other tools. Then we pass in our block dangerous bash function as the hook callback. So the flow is, whenever the agent is about to run a bash command, this hook gets called first. If the command contains rm-rf, it denies the operation. Otherwise, it returns an empty object, and the command is allowed to continue unchanged. A production version would match a list of dangerous patterns rather than a single substring, but the shape is exactly this. Note the precedence rule for when several hooks weigh in on the same operation. Deny beats defer beats ask beats allow. If any hook returns deny, the operation is blocked, period. This diagram shows what happens when multiple hooks weigh in on the same operation. The SDK resolves hook decisions by priority. First, it checks whether any hook returns deny. If even one hook says deny, the operation is blocked immediately. If no hook denies, it checks whether any hook returns defer. In that case, the decision is deferred to the next layer of permission handling. If no hook denies or defers, it checks whether any hook returns ask. That means the user gets prompted for approval. And if none of the hooks return deny, defer, or ask, the operation is allowed to proceed. So the key rule is the most restrictive hook wins. Deny beats everything, then defer, then ask, and only after all of those are absent does the operation proceed. Demo 2. Inject live context into every prompt. If pre-tool use blocks, user prompt submit informs. This hook runs before the model sees a prompt and appends information to it through additional context. The classic use is grounding the agent in facts it cannot know from training: today's date, the current Git branch, and the environment it is running in. This allows you to inject live context into every prompt. This is the essence of context engineering. This hook shows a different pattern. Instead of blocking a tool call, it injects live context before the model sees the user's prompt. It runs a quick git command to find the current branch, then combines that with today's date. The important field here is additional context. That text gets appended to the prompt the model receives, so the agent is grounded in information it would not know from training alone. In this example, every prompt can be enriched with something like today's date and the active Git branch. So the big idea is pre-tool use hooks control actions before they run, while user prompt submit hooks can enrich the model's context before it responds. This one is shown in Python only. The TypeScript shape is the same object with camel case keys. Register it under user prompt submit with no matcher, since prompt events have no tool to match against. Gotcha. It is tempting to write a user prompt submit hook that spawns a subagent or kicks off another query to enrich the prompt. Be careful. If that work submits another user prompt, it can trigger the same hook again, and you have built a recursive loop. Keep prompt submit hooks to cheap synchronous enrichment, such as reading a file or running a fast git command, and never let them re-enter the prompt path. Demo 3. Audit every file edit. Post-tool use runs after a tool returns, which makes it the natural home for logging. This hook appends a line to a JSON-L audit trail every time the agent writes or edits a file, exactly the kind of record that compliance and debugging both want. Since it only performs a side effect and does not need to influence the agent, it is a clean fit for the pattern. This hook is for auditing. Unlike the earlier bash hook, it does not block or modify anything. It runs after a tool has completed and records what happened. The hook builds a small audit entry with 4 fields: the current UTC timestamp, the tool name, the file path from the tool input, and the session ID. Then it appends that entry to audit.jsonl, one JSON object per line. Finally, it returns an empty object, which means there is no decision to make. The hook is just performing a side effect. This pattern is useful for file writes and edits because it gives you a durable trail of what the agent changed, when it changed it, which tool made the change, and which session it came from. Register it under post-tool use with a write/edit matcher so it logs only file mutations. If you genuinely do not need the agent to wait for the write, you can return an async output, which is async_true in Python and async true in TypeScript, so the logging happens in the background. The catch: async outputs cannot block, modify, or inject anything, because by the time they run, the agent has already moved on. Use them for logging, metrics, and notifications only. The output object, and the one field placement that trips everyone. Every callback returns one object with 2 tiers, and getting the tiers right is most of what goes wrong with hooks. Top-level fields affect the conversation. System message surfaces a message to the user, and continue underscore in Python controls whether the agent keeps running. Hook-specific output affects the current operation, and its valid fields depend on the event. Returning empty brackets always means allow, no changes. This diagram breaks down the shape of a hook's return value. A hook returns one output object, but that object has a few different layers. At the top level, you have fields that affect the broader conversation. System message displays a message to the user, and continue controls whether the agent keeps running. In Python, that field is written as continue underscore because continue is a reserved keyword. Then there is hook-specific output, which is where the hook controls the current operation. That is where you put fields like permission decision, which can deny, ask, or allow an operation. You can also include permission decision reason, which explains the decision so the model can adapt. For prompt hooks, additional context is the important field. It appends extra information to the prompt the model receives. And for tool use hooks, updated input can rewrite the tool arguments before the tool runs. The key gotcha is that updated input belongs inside hook-specific output, and when you use it, you also need to set permission decision to allow on the same object, or the modified input will not be approved. Putting updated input at the top level is the single most common hooks mistake, and it fails silently. The tool just runs with the original input as if your hook did nothing. Also, always return a new input object rather than mutating the one you received. Where hooks run, and why that cuts both ways. One architectural fact shapes everything about using hooks well. Programmatic hooks run inside your application's process as direct callbacks. This has a great upside and a real downside, and you should hold both at once. The upside is that hooks do not consume the agent's context window. A post-tool use audit hook can log a megabyte of detail, and the model never pays a token for it, because the logging happens in your process, not in the conversation. That is exactly why hooks are the right tool for heavy logging and validation that you would never want bloating the prompt. The downside is that because the hook is your code in your process, an exception in a hook can crash your application, and a slow hook stalls the agent. The default timeout is 60 seconds per matcher. A hook that makes a network call on every pre-tool use will make the agent feel sluggish, and an unhandled error in a hook takes down the run. Treat hook callbacks like production code in a hot path. Guard against exceptions, keep them fast, and push anything slow into an async output or a background queue. Do this today. Write a pre-tool use hook on Bash that blocks at least one destructive pattern and confirm it holds even under bypass permissions. Pair every deny with a permission decision reason that tells the model why, so it adapts instead of retrying the same blocked command. Add a post-tool use audit hook with a write/edit matcher that appends to a JSON-L trail. You will want that record the first time you debug a session. Audit your callbacks for the updated input mistake. If you rewrite tool arguments, confirm updated input sits inside hook-specific output next to permission decision allow. Wrap each hook body in exception handling and keep it fast. A hook runs in your process, so a crash there is a crash everywhere. The takeaway. Hooks are the difference between hoping the agent behaves and guaranteeing it does. They fire deterministically at fixed points in the loop, run your own code, and decide outcomes without consulting the model. Pre-tool use to block or transform before an action. User prompt submit to inject live context, and post-tool use to audit after the fact. Keep three things straight and you will avoid nearly every hooks bug. Updated input goes inside hook-specific output alongside permission decision allow. Deny beats everything when hooks disagree. Your callbacks run in your process, so they must be fast and crash-proof. Python users, remember that session start and session end are shell command only. Permissions ask for permission. Hooks ask no one. Once you have written your first pre-tool use deny and watched it hold under every mode, you will not ship an agent without one again. Here are 25 key ideas from the article. Permissions help, but they still depend on model judgment and user approval prompts. Hooks are stronger than permissions because they run as your code at fixed points in the agent loop. A hook can block an action regardless of what the model wants to do. Hooks give the application the final word on agent behavior. The core message is permissions ask for permission. Hooks enforce rules. Hooks can block dangerous operations before they run. Hooks can inject fresh runtime context into the model's prompt. Hooks can transform tool inputs before a tool call executes. Hooks can audit actions after tools run. A hook firing follows a pipeline. Event fires, SDK gathers hooks, matchers filter them, callbacks run, and outputs tell the agent what to do. Hooks are registered by event name, such as pre-tool use, post-tool use, or user prompt submit. Matchers filter hooks by tool name, not by file path or tool arguments. To filter by file path, command content, or other arguments, the callback must inspect tool input. The main lifecycle events are session start, user prompt submit, pre-tool use, post-tool use, stop, and session end. Pre-tool use is the main event for blocking or modifying actions before they happen. Post-tool use is the main event for logging, auditing, and observing tool results after they happen. User prompt submit is useful for injecting context before the model sees the user's prompt. In Python, some lifecycle hooks, including session start and session end, are not supported as programmatic callbacks. They are TypeScript only in that form. The first demo blocks dangerous bash commands like rm-rf. A blocking hook returns permission decision equals deny inside hook-specific output. Permission decision reason matters because it tells the model why the action was blocked, helping it adapt instead of retrying. When multiple hooks weigh in, the precedence rule is deny beats defer, defer beats ask, and ask beats allow. A hook return object has two main tiers, top-level fields for conversation behavior and hook-specific output for the current operation. Updated input must be placed inside hook-specific output, and it must be paired with permission decision equals allow. Hooks run inside your application process, which is powerful but risky. They do not consume context window tokens, but slow hooks stall the agent and unhandled exceptions can crash the run.
About the author, Rick Hightower, Claude Certified Architect. Rick Hightower helps companies become AI first through practical mentoring, executive and team training, and custom AI solutions development. He is a former senior distinguished engineer at a Fortune 100 company, where he focused on bringing ML and AI insights into real frontline business applications. Rick is a Claude Certified Architect, AI systems practitioner, and builder of production multi-agent systems. He is currently working on authoring a book on harness engineering with Manning Publishing. He created Skilz, a universal agent skill installer supporting 30-plus coding agents, including Claude Code, Gemini, Copilot, and Cursor, and co-founded one of the largest agentic skill marketplaces. Today, Rick and the Spillwave team works with leaders and teams who want to move beyond AI experiments and build real AI capability inside their companies. He helps organizations adopt AI safely, train their people, redesign workflows, and build practical AI systems that create measurable business value. Ready to make your company AI first? Connect with Rick with the links in the video description. LinkedIn, Substack, or Medium. Book him to speak or train your team, or visit Spillwave to explore mentoring, training, and custom AI solutions for your organization.
Thanks for watching.